This is section 5.5, which is called Hess's Law. So now what we're going to do is we're going to look at a particular type of problem involving the addition of chemical reactions. The idea here is the following. Imagine that you wanted to know how far it was from point A to point B. One way you could figure that out would be to go from point A to point C, and then from point C to point B. Those two distances added together would be equal to the distance between A and B, right? Now, the same holds true for enthalpy changes. It turns out that we can add enthalpy changes for individual steps to figure out what the enthalpy change is for an overall step. Okay, so I'm going to show you what I mean by that. An example is, suppose we take methane, CH4, which is in the gaseous state, and react it. So we're going to take 1 mole of it and react it with 2 moles of oxygen gas to form a mole of carbon dioxide gas and 2 moles of liquid water. The enthalpy change for that has been measured, and it's negative 890.4 kilojoules per mole. That's an exothermic reaction, right? So that means it's releasing energy to the surroundings. Okay, well, what if we take another, this is a physical change, but it's essentially a reaction. 2 moles of liquid water, and we're going to boil them. We're going to vaporize them into 2 moles of gaseous water. That has a measured enthalpy change of 88.0 kilojoules per mole. The question is, what would happen if we combined those two processes? So let me show you a little picture here. So imagine it this way. Imagine this is enthalpy H, and what I'm going to do is I'm going to put my reactants up here. So methane plus 2 moles of oxygen. And then I'm going to note that the enthalpy of carbon dioxide and liquid water is lower than that. Okay? Essentially, it's the energy content. The energy content of CO2 and 2H2O liquid is lower than the energy content, or the enthalpy, of CH4 gas and 2 moles of O2. And that difference in energy is 890.4 kilojoules. And remember, earlier we said that delta H is H final minus H initial. So the final enthalpy is lower than the initial enthalpy, so that difference is negative, right? So now suppose then we do a second step and we go up to here, just a little bit. But essentially what we do is we convert that to CO2 gas and 2 moles of gaseous water. Notice that's a little bit higher in energy. It's higher in energy by 88 kilojoules. There's a difference in energy of 88 kilojoules. So really then what we're asking is, if it's 890.4 kilojoules from methane and oxygen to carbon dioxide and liquid water, and it's 88 kilojoules to carbon dioxide and gaseous water, what's the difference between these two levels here? I'll do a dashed line. What would that be? All you would do is you would just add these two numbers together. You'd add the negative 890.4 and the 88, and that would give you your answer. And that's essentially what we're going to do. So now let me show you how we represent this in terms of chemical equations. When we add chemical equations, what we do is we add the reactants from the equations we're adding together. So for these two reactions, we would add methane, oxygen, and liquid water. Then we add the products together, carbon dioxide, liquid water, and gaseous water. And then we add the enthalpies, okay, the enthalpy changes. So let me do that here. CH4 gas, 2O2 gas, 2H2O liquid. Those are all the reactants, right? We're going to add those together. And then we're going to add all the products together. CO2 gas, 2H2O liquid, 2H2O gas. Okay? Add the reactants and add the products. Now notice that there is 2 moles of liquid water on both sides. So just like an algebraic equation, we can cancel them. Anything that's identical on both sides, we can cancel. So this now simplifies to CH4 plus 2O2, forms CO2 and 2H2O gas, right? Now, what do we do in terms of the enthalpy changes? Well, the enthalpy change for this would just be the enthalpy change of the first step plus the enthalpy change of the second step. And there you go. Isn't that simple? What we're claiming is that if you add 2 equations together, you just add the enthalpy changes. Now in practice, when you do Hess's law problems, they're a little bit more challenging than that. They're going to give you some little puzzles you have to solve. But that's essentially the idea, is that if you add equations together, and we could add as many equations as we want. I just did 2, but we could add 4 equations, 5 equations, 6 equations. You just add all the reactants together, you add all the products together, and then you add the enthalpy changes, and that gives you the enthalpy change for a process that you didn't have to begin with, right? We knew the enthalpy change for this one and this one, but we didn't know what the enthalpy change for this one was. This shows us a way to do it. We add the enthalpy changes for the equations that we know, and that gives us the enthalpy change for the equations that we don't know. Now, I am going to point out a couple things in here. This is not really discussed in this section, but it's shown in these sample problems. So you'll definitely see it in the sample problems. But I want to make a couple of points. One is sometimes it's the case that we have to reverse an equation in order to add them together. If we're going to reverse an equation, so for example, A goes to B, and let's say delta H, I'm just going to make up a number here, is plus 500 kilojoules per mole. If for some reason we reverse the equation, and now B is the reactant and A is the product, we reverse the sign. You just change the sign of delta H. So if you reverse an equation, you change the sign for delta H. Okay, very simple. Second issue is that you might have to multiply an equation by a constant. That constant could be 2 or 3 or 4, it could be half, a third, whatever it is. That sometimes happens. So here's an example. Suppose I have A goes to B, and delta H, again, is 500 kilojoules per mole. Let's say I want to multiply the equation by 2 and make it 2A goes to 2B. All we would do is multiply delta H by the same number. Okay? That's all we're saying. If you multiply the equation by the constant, you multiply delta H by the same constant. Okay? Now, that also goes for fractions. So for example, if I now multiplied this one here by half, 1/2 a goes to 1/2 b. Well, you'd multiply delta h by half. And it would be 250. Okay, simple as that. If you reverse an equation, you change the sign of delta h. Okay. If you multiply the equation by a number, you multiply the delta h by that number. And if you add equations, you add the delta h's. So those are the three sort of rules, if you want to think of them as that, for how we deal with Hess's law. Hess's law says essentially that if we want to know delta h for some process, if we can combine different equations to give us the equation of the process that we want, then all we have to do is add the delta h's for the known steps, and that will give us delta h for the unknown step that we're interested in. Okay? So this will make a lot of sense when you start looking at practice problems and sample problems.